Today we will discuss the optical microscope characterizations of the nanomaterials. Now we will see that we see the small particle with the optical microscope generally, but at nanoscale these are not fit to observe the particle because the smallest resolvable distance between the object is half the wavelength of the light used. For visible light, it's 500 nanometers, and the resolving power is 250 nanometers only. Nanomaterial 100 nanometer would appear blurred and undistinguishable, so these cannot be used. Only the wavelength from UV, X-ray up to gamma rays are applicable for visualizations of the characterizations. Now, for this, generally we use the electron beam. Why beam we are using? Because the de Broglie relations tells us that the lambda is equal to h upon mv. Here v is the velocity. We see that velocity is related with the energy. Energy is related with the voltage. If we keep the voltage 50,000 here, and then wavelength is 0.0055 nanometers, when the velocity is 1.326. So again, when we increase the 10 lakh velocity, electron volt energy is given to this, and the speed is 593 into 10 raised to the power 8 centimeter per second. So we have we can measure the wavelength up to 0.001 nanometers. So small particle can be measured with the help of the electron beam. So for this we generally use the different methods are used to characterize. So first is the transmission electron microscopy. Just see in the figure, this is just like a slide projectors. Here we have a light source, that is the electron gun is this is the electron gun, and we have the two condenser lenses. Then we put the sample inside the slides. Then to focus it we have the objective lens. Then this beam is projected on the projection screen, and hence we can obtain the image. The next type of characterization is the scanning tunneling microscope. That is, scanning tunneling microscope is based on the principle of tunnel effect, and used to get the images of the atomic arrangements of the solid surface that conduct electricities. Just see this figure here. Here is the specimen is taken, then the tape is made up of few angstroms, and then this tape is connected with the device that is known as a piezoelectric transducers. This is the device used to move specimen in nanometers increment. So we can move into x-axis, y-axis and z directions with the help of the piezoelectric transducers. So the sample is connected with the tunneling current. So here is the tunneling current that is connected to the computer or measuring device. The tunneling current can be measured and computers with them. And in the following graphs, it shows that the tunneling current versus probe tip. We know that the specimen is just like up and downs are there on the specimens. So the path of the tip is kept constant. So when the up path comes up, there is a tunneling of the electron from the specimens to the probe, and hence the tunneling current rises. And when there is a downward path we have, then the tip of the do not conduct the electron, less electrons are conducted, and hence the tunneling current is less. Here again we take the same situations, but here we move the tip ups and down, shown by the dotted lines, but the tunneling current is found to be constant. Just as the sample is increasing or decreasing, in the similar way the tip is moved along with the specimen, and the constant current is obtained as shown in the dotted line, or as shown in the solid lines. So this is the STMs. So applications of the STMs are The tip of the STM can move the molecule one by one to make a structures damaging the bonds. Using a scanning tunneling microscope, one can make the observation of individual atom on the surface of the conductor of the sample. This technique is used to study the DNA molecules. Thirdly, it can be used to capture the density of the distribution of the surface state electrons. So these are the mainly three uses here. Then here is the again brief theory of the scanning tunneling microscope. That is, the STM is used the quantum physics phenomena. That is, the tunneling to prove the detailed image of the substance that can conduct the electricity. The probe is brought with a few angstroms of surface of the materials, and the small voltage is applied between surface and the premise. This is the working of the STMs. Because the probe is so close to the surface, the electron leaks a tunnel through the gap between probe and surface, generating the current, that is the tunneling current. The strength of the tunneling current depends upon the distance between the surface and the probe. If the probe moves closer to the surface, then the tunneling current increases, and if the moves away from the surface, then the tunneling current decreases. As the scanning machine moves along the surface, the magnetism constantly adjusts the height of the probe to keep the tunneling current constant. By tracking these minute charges, a computer can create a 3D representation of the surface. Here is the difference between the SEM versus TEM. That is the SEM versus TEM is the scanning electron microscopes, just like STM. Scanning tunneling microscopes. Sample may be conducive or else it will be worms. That is, the sample must be conductive, otherwise the sample may burn. In the TEM, what we have, the sample must be thin enough or else it won't project the recognizable image. So, second difference is in the SEM the image is 3D, whereas in TEM image is 2D. Number 2, it over 300 kilo times magnifications, but here the 1 million times the magnifications. The magnification in TEM is more, but image is 2D. So here is and the third method is the atomic force microscopy. As the metal probes in an AFM moves along that is also known as the atomic force microscopy, moves along the surface of the sample, the electron in the probe are repelled by the electron of the atom in the sample, and AMF adjusts to the height of the probe to keep the force on it constant. By the up and down movement of the probe, a computer can make 3D images of the surface sample. Here is the structure of the AFM, atomic force microscopies. AFM microscopy. Here is the laser beam is incident on it, and there is a position detectors. Here is the tip of the probe, and when the tip of the probe is connected with the cantilevers and moves on the surface, and that is photodiodes. Laser beam is went to the photodiodes and they get detected by the detectors. And here is the colored image of the cantilevers, and laser beam is incident with the red light, shown in the red light, and the surface of the nanomaterial is shown as with the just watercolors, and here is the tip which tunnels over the surface. That is the scanning probe microscopy is found here. Thank you.